admit huko.
YouTube live. Yeah, no, that's
Ni recording.
it's not a recording, it's a live session. Oh.
Okay, so I hope everybody is okay. So far, to the best of my knowledge, the topics that you've covered in chemistry, you only did about 4. You have 4 tutorial sheets, but before you dive into the tutorial sheets, you need to check out, you do have the solutions for Cat 3. So when you are preparing for this, for your exams, make sure you look up those. So you check out the solutions for Cat 3, and also you check out those solutions for the Cat 4. So make sure to say you have I don't have your Cat 3 and your Cat 4 papers, but then I'm sure they will share to you, to your WhatsApp groups in the last semester. So you check the solutions for Cat 3 and also check out the solutions for Cat 4. So for today, we're going to start with tutorial sheet number 4. So we're going to start with tutorial sheet number 4. Tutorial sheet number 4. So tutorial sheet number 4 is the one that we're going to start with. I'm going to share the tutorial sheet later with you guys. So tutorial sheet number 4 is the topic is atomic structure. Okay, so the topic is atomic structure and periodicity. So now, before we start solving the questions from the tutorial sheet, I'm going to give you a comprehensive summary, just the key concepts that you need to know when dealing with the topic atomic structure and periodicity. So, a comprehensive summary of this topic, there are only about 6 things that you need to know. So, number 1, we're going to start with those key concepts. So I'm just going to give you a summary and then we're going to solve some selected questions from the tutorial. So the first thing that we need to know under atomic structure and periodicity. So first, this topic is covered in tutorial number 4. And then this is the topic. Now I'm going to give you a summary of the same topic. So the first thing that you need to know about atomic structure and periodicity is this terminology. Okay, so the first concept that you need to know is the concept of electromagnetic radiation. So what do they mean by electromagnetic radiation? So the other name or the other term that is used in place of electromagnetic radiation, we just need to say light waves. So electromagnetic radiation just refers to the form through which energy travels through space. So the form in which energy or light travels through space is called an electromagnetic radiation. So it refers to the form in which light travels through space. Now light or energy can travel through space in several forms. So the first form that energy can travel through space is in form of gamma rays. Examples of those electromagnetic radiation, we have gamma rays, we have X-rays, and the UV light from the sun. You also have microwaves. Micro means something which is small, and then wave. So meaning, because these That's the reason why they are called microwaves. So examples of electromagnetic radiation or examples of light waves, we have gamma rays, X-rays, UV light, that is the sunlight energy, the radio waves, and microwaves. Okay, so now all electromagnetic radiations have three primary characteristics. The primary characteristics of electromagnetic radiation is that they have speed. They do travel at a constant speed, and then they also have frequency and wavelength. All electromagnetic radiations have three primary characteristics. Number one, they do have frequency. Number two, they do have wavelength, and then they all travel at a constant speed of light, which is 2.9979 times 10 to the power 8. So the characteristic of electromagnetic radiation can be the relationship among the characteristics of electromagnetic radiation can be represented using this formula. So this is the first formula that you need to know when dealing with this topic. So this is a lowercase bit letter no. So it represents frequency. So frequency is equal to the constant speed of light, which is c, divided by the lambda, which is just a designation for wavelength. So we just say where this is just a frequency. So these are the characteristics of electromagnetic radiation. They have frequency, they have wavelength. So they do have wavelength. Now wavelength is just a distance between two consecutive peaks of a wave. So what they mean is that okay, so this is a designation of a wave. It's a diagram representing a wave. So the highest points of a wave, is these 2 points. So now the distance between the highest points of a wave is called what? Wavelength. Check out, it consists of two terms, wave and also length. Meaning it's just the length of the wave, the length of a wave. So wavelength is just the distance between two consecutive peaks of a wave. The units of wavelength is supposed to be what? In meters. Now in most cases, when you're dealing with this topic, wavelength, in most cases, they are going to give you in nanometers. So now you just need to convert it back to what? To meters. So if they give you wavelength in nanometers, let's say 435 nanometers. So if the wavelength has been given to be 435 nanometers, all you need to know is that you need to convert from nanometers back to meters. So a nano is just an SI prefix. That means 10 to the power -9. So the easiest and most fastest way of how you can convert from a nanometer to a meter is that you just bring down your 435. Where there is a nano, you just say times 10 to the power -9, and then you are remaining with the meter like that. So that's one of the ways on how we are going to give you with the units of nanometers. And then the second unit that is commonly used is angstrom. Angstrom is just A with a knot on top. So angstrom, if you want to convert from angstrom to meters like that, angstrom is just 10 to the power -10. So if the wavelength has been given to be 435 angstrom, in meters you are going to say 435. Why is it angstrom? You say times 10 to the power -10 in meters like that. So the two common units they use nanometers and also angstrom. So now the relationship among the three primary characteristics of electromagnetic radiation can be represented using this formula. So the frequency is given by the constant speed of light divided by what? The lambda. So the units, this side the units is supposed to be meters. This side the unit of frequency is supposed to be hertz. And then C we've already established to say it's just the constant speed of light. So now the constant speed of light is just 2.99. Of course, because this one is a constant, they are going to give you in the exam, or 2.99 times 10 to the power 18 meters per second, like that. So this is the constant speed of light. Okay, so the first stuff that you need to know on atomic structure and periodicity is that you have electromagnetic radiation. And electromagnetic radiation, it just refers to the form through which energy travels in space or through space. So energy can travel through space. Examples of electromagnetic radiation, you have gamma rays, UV light, radio waves, microwaves. So those are examples. Now, what do these electromagnetic radiations, the gamma rays, the UV light, the radio waves have in common? So what they all have in common is that they all have frequency. They all travel at a constant speed of light, and they do have what? Wavelength. So now these, they make the three primary characteristics of what? Of electromagnetic radiation: frequency, wavelength, and speed. So the relationship is represented using this formula. Okay, so number 2, the second stuff that you need to know, number 2, about electromagnetic radiation. So the second stuff that you need to know about electromagnetic radiation, number 2, we talk of quantization of energy. Okay, so we talk of the quantization of energy. So in 1900, there was a German physicist by the name of Max Planck. So Max Planck postulated that energy can either be lost or gained in small discrete whole number values of hv. So now, the energy that is possessed by a single photon, a photon is just a basic unit of light. Now, you see, when you look at the rays of light, a ray of light just appears to be more like a straight continuous line like that. Now, in this ray of light, there are small particles, discrete particles that are moving at a fast speed, the speed of light, which is 2.997 and then 10 to the power 8 meters per second. So now, the energy that is possessed by this single photon, a photon is just a small discrete package of light. So a discrete package of light is called a photon. Now the energy that is possessed by this single photon can be calculated using delta E. So this means delta means change. So change in energy is equal to H multiplied by the frequency. H is the Planck's constant. Frequency, we do not say frequency. Frequency is equal to frequency is equal to what? The constant speed of light divided by what? The constant speed of light divided by what? The light. So this formula can be modified where you see the frequency, we can substitute with this, generating this formula. So change in energy is equal to H, which is the Planck's constant. Where there is a frequency, we can put formula number 1. So Hc divided by what? By lambda. So make sure you know this formula, it's going to be used more often in solving questions. So let's take out delta E is just change in energy. Delta E change in energy. So change in energy is measured in what? In joule, right? Okay, delta E is change in energy, and then H is just the Planck's constant. So H is Planck's constant. Planck's constant is just 6.626 times 10 to the power negative 34 joules second. Okay, so that's Planck's constant. And automatically you do know the speed of light. You already know the speed of light and the wavelength. Okay? So changing energy, Planck's constant, this is the value for the Planck's constant. And then already we have established to say this is a wavelength. And this is the constant speed of light. I've already given you the constant speed of light. Okay, so this is the second important stuff that you need to know when dealing with atomic structure and periodicity. So the first formula is this one, formula number one. Frequency is equal to the constant speed of light divided by what? The wavelength. And then the second most important stuff is this formula. The change in energy is equal to the Hc divided by what? The wavelength. Keeping in mind to say these two are constant values. So Planck's constant 6.626 times 10 to the power negative 34 multiplied by the constant speed of light, you already have it. And then the wavelength, you need to keep in mind to say they will give you in other units, just convert them back to nanometers. Okay, so let's move on to the third most important stuff that you need to know. Let's talk about the Bohr model. So the Bohr model, I've skipped the photoelectric effect, and I've also skipped the Broglie's wavelength. Those ones, they are not too common, not too. Moreover, this is just a summary of the key points or key concepts that you just need to know for you to just get comfortable with the topic in the shortest period of time. Okay, so number 3. Let's go for the Bohr model now. So we talk of the Bohr model. Okay, so in 1921 there was a Danish physicist called Niels Bohr. So now for Niels Bohr, he just postulated to say an electron in the hydrogen atom is found circulating around the nucleus in certain allowed orbits. If you remember or recall back in high school, where you find an electron, when you find electrons, we used to do some electron configuration. Electrons, you find them in what? In shells. So you find an electron, we used to configure electrons like that. We never used to configure electrons where you put them in between what? In between shells. No? But electrons will be found circulating the nucleus in what? In shells or orbits. Certain circular allowed what? Orbits. So these shells, this is the shell. These shells, now we do call them what? Now we do call them orbitals. The other interchangeable term that is used to represent a shell or an orbital is just called energy levels, or principal quantum levels. Okay, so now according to Niels Bohr, an electron in the hydrogen atom orbits around the nucleus in certain allowed circular orbits. Okay? So an electron in the hydrogen atom circulates around the nucleus in certain allowed circular orbits. So the energy that an electron is going to emit or absorb as it moves from one energy level. If an electron is moving from one energy level to another, it loses or gains energy. So the energy that an electron is going to possess can be calculated using delta E. Change in energy is equal to negative 2.178 times 10. To say this, in this case, I have to use the Bohr model or not. If they've said calculate the energy emitted by an electron as it moves from, let's say, n is equal to 3 to maybe n is equal to 4. Okay. So when they've given you two values of n, you would not say the first value is going to be the initial, the second value is going to be what? At the final. So n is equal to 3 to n is equal to 4. So the final will be 4 squared minus the initial, which is what? 3 squared. This is just the constant value. Okay. So this is the Bohr model. So the formula that we need to use. So now we need to keep in mind to say when an electron is moving from a lower energy level to a higher energy level. So when an electron is moving from a lower energy level to a higher energy level, meaning maybe n is equal to 4, energy is absorbed. Okay. So when an electron is moving from a lower energy level to a higher energy level, the energy is going to be what? Absorbed. And the value for E is going to be what? Positive. Okay. When an electron is moving from a higher energy level, let's say 7, to a lower energy level, energy is going to be what? Lost. And the value for delta E, the sign for delta E is going to be what? Negative. So let's say, if you want to know to say, okay, what I'm doing is the right thing. In most cases, you're going to get delta E. If you're moving from a higher energy level to a lower energy level, let's say you're going to get delta E is equal to maybe negative 2.42 times 10 to the power negative 19 joules. Energy is measured in joules. So how do you know to say what I've done is correct? You look at the power of the exponent. In most cases, when you are dealing with the Bohr model, the value for the energy will have an exponent powered by what? Negative 19. If you get something like negative 26 or something higher or lower, you just need to recheck your calculations. You might have error somewhere. So most of the time you just get this negative 19. So what happens when you do get negative? You need to keep in mind to say you do not have negative energy. Energy is only negative to indicate to say an electron is moving from a higher energy level to a lower energy level. So meaning you're just saying energy. So when you get a negative, just say energy has been what? Lost. And then you just drop the negative, it becomes 2.42 times 10 to the power negative 19 joules. Okay, like that. And then the other most important stuff that you need to know about this topic is the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle. So this is the Bohr model for the first stuff that you need to know. The other stuff is the Heisenberg uncertainty principle, number 4. So the Heisenberg uncertainty principle. This one talks about the fundamental limitation. So according to the Heisenberg uncertainty principle, we can't know these two things. We can't know the momentum and the position of a moving particle. We can't know the momentum and the position of a particle simultaneously. We can't know them at the same time. You can know one of the two things. You can either know the momentum and then the position you will not know, or you will know the position of the particle, but then you will not get the momentum. So I think this is the last answer. Let me check out some questions and then we close. So number 4, the Heisenberg. So the Heisenberg uncertainty principle. So Heisenberg uncertainty principle. So this principle states that there is a fundamental limitation to just how precise we can determine both the momentum and the position of the particle. So this states that the Heisenberg uncertainty principle states that there is a fundamental limitation to just how precise there is a fundamental limitation to how precise we can determine both So there is a fundamental limitation to just how precise we can determine both the position and the momentum of a particle. So now, according to this principle, the change in position, delta x, so delta means change, and x means the position. So delta x, change in moment, change in position multiplied by the change in momentum. So momentum is denoted by lowercase Greek letter rho. So change in position multiplied by change in momentum is greater than or equal to the Planck's constant divided by 4 pi. So change in position multiplied by change in momentum is greater than or equal to the Planck's constant divided by 4 pi. Now, you did learn in physics to say momentum is given by the mass of a particle multiplied by the velocity at which the particle is moving. So this formula can then be modified. So change, the formula can then be modified as change in position delta x multiplied by, because momentum is given by the mass multiplied by velocity. Notice to say it's not dating, so this it will mean to say frequency. Just as v represents the velocity, it's greater than or equal to the Planck's constant divided by 4 pi. So this is the Heisenberg uncertainty principle. Okay, I think for today this will be enough. Now let's just check out two questions from the theory sheet. You can check out theory sheet number 4. Theory sheet number 4, we are going to solve question number 1. We're going to skip question number 3, 4, 5. We jump to question number 6. Yeah, and then we close. Okay, so question number 1, 2, and question number 6. So if you don't mind, I can grab. Okay, so we'll check out question number 1 from tutorial sheet number 4. Is everybody okay? Like, do you have any questions, or is there some clarity that you want? Or if you missed a concept, if you missed it, you can just ask, or you can just speak out. Okay, so everybody, I guess they're okay. Okay, so question number 1. So question number 1 is saying the wavelength of a photon of light emitted from the heated copper-1 chloride crystals was found to be 862 nanometers. Calculate the frequency of this light. So question number 1. So the wavelength was found to be 862 nanometers. The wavelength is denoted by the lowercase Greek letter lambda. Had been given to be 862 according to this time, 862 nanometers. Calculate the frequency of this light. So the question is wanting us to calculate the frequency. So the frequency we do not know. And of course, because it's light, it will travel at a constant speed. So the constant speed of light is, I've already given, is 2.9979 exponent 8 meters per second. Okay, so they're saying calculate the frequency. Now, each and every time they give us the wavelength, you need to check out the units. Now, if the units you've noticed to say it's nanometers, where there is a nano, you just put 10 to the power negative 9. Your meter just drops this side. Your value is 862. You even put less. So we've converted from a nanometer to a meter. Now, when calculating for frequency, we do notice the frequency is equal to the constant speed divided by the wavelength. Now, the constant speed, we've already established 2.9979 times 10 to the power 8 meters per second divided by the wavelength. So, the wavelength they've given us is what? 862 times 10 to the power negative 9 is what now? It's in meters. Now, if you can see the units, the meter and the meter cancels out. Here you're going to remain with me a per second. Now, a per second is just the same or equivalent to a hertz. Okay, so quickly, if somebody has a calculator, you can just punch this and then you get your answer. So if you need to be comfortable, if you want to be comfortable to avoid any errors or injuries when dealing with this topic, how you punch in the calculator, just punch, open parentheses, open brackets, then you enter the speed of light, 2.99 times 10 to the power 8, you close the brackets, and then punch the division sign. So divided by, you punch, you press, and then you open parentheses, you enter everything, you close. So the answer that you're going to get, please again, when dealing with frequency, in most cases you're going to get something answer, then times 10 to the power, you're going to find times 10 to the power 14. If you get an exponent maybe to the power, any exponent which is above, greater than or equal to, greater than 14 or less than 14, you need to recheck your calculations. So in most cases, this is what you get for your frequency. So you punch, unless if somebody has a calculator. I don't have a calculator myself. So you finish up the calculation. Okay, so now we can check out question number 2. So question number 2 is saying a photon of UV light possesses enough energy to mutate a strand of human DNA. What is the energy of a single UV photon having a wavelength of 278 nanometers? Okay, so a photon of UV light, ultraviolet light, possesses enough energy to mutate a strand of human DNA. So this is question number 2. Question number 2 is saying a photon. So we're dealing with question number 2. Let's do our data collection. So data. A photon of UV light, a photon of ultraviolet light possesses enough energy to mutate a strand of human DNA. What energy of a single UV photon having a wavelength? So the wavelength of this photon has been given to be 278 nanometers. Now they are saying what is the energy? So they want delta E. What is the energy? We do not know. So now because they are talking about a photon or they are talking about light, we do not to say all light waves or all electromagnetic radiation, they do travel at a constant speed of 2.9979 times 10 to the power 8 meters per second. Okay, so now because we are calculating for the change in energy, delta E, change in energy is equal to the constant, the Planck's constant multiplied by the constant speed of light. Everything is divided by what? The lambda, which is very big. So Planck's constant, I've already given the value for the Planck's constant. This is the constant speed of light, it's already here on top. Divided by what? The wavelength. Now again, with the wavelength, always keep in mind the units. Okay? So you get your nanometer with that. So Planck's constant is 6.626 and 10 to the power -34. Close. Again, open on your calculator. The constant speed of light, which is C, 2.9979 multiplied by 10 to the power 8, again close. Everything will be divided by our wavelength. And our wavelength has been given to be 278 nanometers. Converting it back to meters from a nano, so you get your 278 times 10 to the power -9, your meters would have converted. Okay, so this was question number 2. So you just punch everything in the calculator. Just the way I've written everything down. You open parentheses, punch the values in, close. Open parentheses, punch the values in, close. Everything divided by, open parentheses, punch the value for the wavelength, and then you do what? You close. So the answer that you're going to get becomes your what? The energy that will be required for the photon to mutate a strand of what? Of human DNA. Okay, so question number 1, question number 2 is done. Question number 3 we skipped. They were saying describe the photoelectric effect. So this one I'm going to skip it out. Okay, so for question number 6, it does represent the Bohr model, which is the last concept that we talked about, we looked at. Okay, so let's check out question number 6, the last one, and then we can close. For the other part of the topic, the second part of the topic, we are going to finish with tomorrow in 2 minutes. Okay, so we are not going to solve the entire question number 6 because it has other sub-questions. We have A, B, C, and D. Okay, so from the question, we're only going to select question number B and C. So the question is saying, calculate the wavelength of light emitted when each of the following transitions occur in the hydrogen atom. Calculate the wavelength of light emitted when each of the following transitions occur in the hydrogen atom. So the Bohr model is sometimes referred to as the quantum mechanical model for the hydrogen atom. The Bohr model only holds true when you are dealing with the hydrogen atom. Why? I guess because the hydrogen is the only element of the periodic table that has one electron. Okay, so let's check out question number B. So question number 6, B. So the transition is n is equal to 2. So an electron in the hydrogen atom is moving, so it's transiting from the energy level 2 or principal quantum level 2 up to principal quantum level number 4. Now, what energy is going to be emitted when the hydrogen atom or when an electron moves from n is equal to 2 to n is equal to 4? Automatically, you do know the Bohr model. They are saying, oh, calculate the wavelength. Okay. So what the question is wanting us to get is wavelength. So they want us to get the wavelength, which is lambda. Now, each and every time you see two principal quantum numbers or two energy levels, step number 1, we do not say change in energy according to the Bohr model is equal to negative 2.178 times 10 to the power negative 18, open parenthesis, 1 over n squared final minus 1 over n squared initial. Okay, so automatically this becomes our initial, this becomes our final result. So when we do use the Bohr model, we are going to get the n. Now remember, change in energy is equal to what? The Planck's constant divided by the constant speed of light divided by the lambda. So we are going to have the change in energy from the Bohr model. Okay? And this we already have it, because these are just constant values also. So you do have the Planck's constant, the constant speed of light, all will be calculated for its what? The wavelength, which the question is wanting us to find. Okay, so let's finish up. So changing energy is equal to 2.178 and 10 to the power negative 18, open brackets, 1 over, it's 4, the final what? 4 squared minus 1 over, the initial is just 2 squared. Okay, so 4 squared is 16, 2 squared is just 4. So 1 over 16, so how you punch is this? 1 over 16 minus 1 over 4. You get the answer. So when you do get the answer, multiply the answer by negative 1, by negative 2.178 and 10 to the power times 10 to the power negative Okay, so because an electron is moving from lower energy level to a higher energy level, the answer that you're going to get will be positive. Because I do not have a calculator, but then the answer should be 2.45 times 10 to the power negative 19. So energy is always measured in what? In joules. So you get something like 2. Something like this. So you need to keep in mind to say each and every time when an electron is moving from a smaller number to a higher number, or from a lower energy level to a higher energy level, you need to know to say energy is being what? Is being absorbed. Because energy is being absorbed, so meaning the value for the energy is going to be positive. So if energy is being released or given out, the value for the energy is going to be negative. So after getting the value for the energy, which is this, you move to the second part of the question. Because the question is wanting us to get what? The wavelength. So how do we get that? So you found the wavelength. So you just make wavelength the subject of the formula. You just interchange the two. So how do you do that? So this wavelength will be equal to the Planck's constant, the constant speed of light divided by what? Changing energy like that. Okay. So after solving, after manipulating the formula like that, you just plug in the values. The Planck's constant I've already given you the value 6.626 times 10 to the power negative 84. And the constant speed of light, you know the value. The constant speed of light 2.99, or you can just say 3 times 10 to the power 8. Everything divided by the change in energy. The change in energy, we just assume this, so we got 2.45 times 10. In most cases, like what we would say, the exponent of energy is supposed to be power negative 19. So negative 19, exponent of negative 19 is the value that you're supposed to get. So if you get something negative 26, you need to recheck your calculation, your budget. That's the reason why I told you to say, if you want to be comfortable with this topic, make sure to say you deal with what? Brackets. So you open brackets 1 over 16 minus 1 over 4. And the answer that you're going to get, you multiply it with the constant value of Z. So after a series of calculations, when you do punch on the calculator, you will get wavelength. If I remember correctly, like the exponent was times 10 to the power negative 6 somewhere there. Okay, so that's how you go about such calculation using the formula. Okay, so the last question, which is question number C. The reason why I picked out question number C is because it has n final infinity. So question number C. First of all, do you guys have any questions? Do you have any questions? Okay, so then let's check out the last one. So question number 6C. This time around, this electron was moving from n is equal to 3, going all the way up to n is equal to infinity like that. So the only difference here is that n final is going to be 1. This time around it's infinity, and the initial is just 3. So as usual, automatically we get the value of the energy. Changing energy is equal to negative 2.178 times 10 to the power negative 18 open. The final is 1 over infinity squared minus the initial is 3 squared. Okay, so now here this is where the 3D parties. Like most people will be looking for the sign or the value of infinity on the calculator, but no, you do not have infinity on the calculator. So this is a mathematics principle. You need to know to say 1 or any number that is divided by infinity. It could be infinity squared or infinity to the power n anything. So any number divided by infinity, everything, the answer is just what? 0 like that. So any number divided by infinity, anything divided by infinity is 0. So the value for the energy becomes delta E is equal to negative 2.178 times 10 to the power negative 18, open parentheses, 1 divided by infinity squared is just 0. Minus 1 over 9, 1 over 9 is, 1 over 3 squared is just 1 over 9. 0 minus 1 over 9 is just negative 1 over 9. Now because there is a negative sign outside, so you do multiply these two, you get the what? A positive answer. Again, it's in line with the same principle that I told you to say. When an electron is moving from a lower energy level, infinity is bigger than 3 So when an electron is moving from a lower energy level to a higher energy level, what happens? Energy is being released, or energy is being absorbed. So the value of energy is going to be positive. So energy is being absorbed. So when you do punch, you are going to get a positive value for the energy. So you punch out, it will be something here times 10 to the power negative 19 joules. Keeping in mind every time the power of the exponent is supposed to be negative 19 in most cases. Actually, in most questions that have been counted so far. So if you get something exponent, again we check your weight. Now, because the question is wanting us or is wanting you to get a wavelength, you use formula for the quantization of energy, formula number 2. The wavelength, after manipulating the formula, changing energy is equal to hc over lambda. Now, because we are trying to get the lambda, so lambda will be equal to the hc divided by what? The change in energy that you will have calculated here. So if you do calculate the change in energy you find, you are just going to plug it in here, like underneath. So if you get a negative value for your energy, keep in mind to say that negative value is only an indication to say energy, an electron is moving from a higher energy level to a lower energy level, therefore energy is being lost. So the negative is an indication to say energy is being lost. So you just drop the negative, and then you're going to use a positive answer. Okay, so far these are the concepts that we've talked about. These are the 3 concepts that we've just talked about. The first concept that you need to know. Let me just give some summary. Okay, so a summary of what we talked about. So number 1, the first concept is that all electromagnetic radiations have 3 primary characteristics. So the relationship among the 3 primary characteristics of electromagnetic radiation can be represented using formula 1. Frequency is equal to the constant speed of light divided by what? The wavelength. Wavelength, keeping in mind, is supposed to be meters. The second concept we've talked about the change in energy. So the energy that is possessed by photon or the energy that is possessed by light can be calculated using hc over lambda. And then the third concept that we talked about talks about the Bohr model. Delta E, change in energy is equals to negative 2.178 times 10 to the power negative 18. Open 1 over n squared final minus 1 over n squared initial. Of course, that is for the hydrogen atom when an electron is moving from one energy level to the next. And then the last concept we talked of Heisenberg principle, which states that there is a fundamental limitation to just how precise we can determine both the momentum and the position of a particle. So the uncertainty in position and momentum is given by is greater than or equal to the Planck's constant divided by 4 or 5. Okay, so unless you guys do have any questions, or if there is something specific that you want us to talk about or discuss, you can just inbox, or you can just post in the group, and then we will come and check it out when we do it for the next session. At this point, we are going to